Okay, hello everyone. My name is Dirk Sudholt.
And I am Mario Alejandro de Fajardo.
And we're going to talk about self-adjusting population sizes for non-elitist evolutionary algorithms and explain to you why success rates matter. So we all know that evolutionary algorithms come with lots of parameters, like the population size, the mutation rate, selection pressure, and so on. And to get the best possible performance out of an evolutionary algorithm, you want to tune these parameters. So how do we find good parameters? One approach is to use parameter control, which means to try and adjust parameters during the run to kind of automatically tune the parameters on the fly. This is at the heart of EAs and continuous optimization. They've done this for decades, but in discrete spaces, it's a rapidly emerging topic because we're just discovering the potential of using parameter control for discrete evolutionary algorithms. There have been some recent runtime analyses with parameter control, like controlling the offspring population size lambda in 1 plus lambda EAs, controlling the number of islands and the migration interval in island models, controlling lambda in the 1 plus lambda comma lambda GA, and controlling the mutation strength in various scenarios like multi-valued discrete spaces, the 1 plus 1 EA and the 1 plus lambda EA. And many of these results showed that the results you can get with parameter control are comparable or even better than results you get with the optimal fixed parameter. So with parameter control, we don't need to know what an optimal fixed parameter is. We can just automatically tune it. And we can even be better than the optimal fixed parameter because the parameters can change during the course of the run and so adjust to whatever is needed. But the problem with these analyses is that these were all about elitist algorithms in quite benign settings, where not much goes wrong when trying a wrong parameter. So we haven't really assessed the full potential of parameter control. And our research question is to dig deeper, ask a more challenging question, and ask, does parameter control work well in more challenging settings? And the setting we're going to look at in our work is to adjust lambda in the non-elitist 1 comma lambda EA. So a simple comma strategy where we create lambda offspring using standard bit mutation and the best offspring survives. Okay, we're going to investigate this on the function OneMax. And this is a pretty hard setting because previous work with John Rowe has shown that there is a phase transition around logarithmic value of lambda, such that if lambda is above this threshold, we get efficient running times of O of n log n, because then in most steps we have elitism because we're creating enough offspring. And if the offspring population size is just a constant factor smaller than this, we get exponential running times. And the reason for that is close to the optimum, most mutations will actually take us away from the optimum. And if we have few offspring, then there's a good chance that all of the offspring will be worse than their parent, and then we're moving backwards. And so the question is whether we can self-adjust lambda to find good parameters to be able to optimize OneMax efficiently.
And well, how did we adjust lambda? Well, we use a generalized 1/5 success rule, where in every successful generation, we decrease lambda by f, and in every unsuccessful generation, we increase lambda by f to 1 over s. What we consider a successful generation is when the offspring, the best offspring, is better than the parent. And what is the intuition behind these success rules? Is that if the algorithm has a success every s plus 1 generations, then the parameter lambda will be maintained over time, because in the successful generation, you will divide 1 time by f, and then later on in the s unsuccessful generations, you will multiply by f to the 1 over s. And overall, all these multiplications and divisions cancel out, and you end up with the same parameter in the end. This parameter control mechanism has been studied before by Doer and Doer in 2018 and Doer et al. In 2019. And does these success rules work? Well, in our work, we find out that if you choose s sufficiently small, so s is smaller than e minus 1 over e, the self-adjusting 1 comma lambda EA solves OneMax in expected O of n generations and O of n log of n expected evaluations. the bound on O of n log of n is the best possible runtime for any mutation-only EAs. And the bound of O of n generations is a small parallel time, which means that this algorithm is able to solve OneMax efficiently. How did we get to this conclusion? Well, we studied the states of the algorithm and how they change. In this graph, we see in the x-axis the value of lambda scaled logarithmically, and in the y-axis, the value of the fitness. So the three possible changes in state of the algorithm is first, in a successful generation, you have an increase in fitness, but you decrease lambda. In a generation where the fitness does not change, you increase lambda because this is considered as an unsuccessful generation. And finally, if you decrease fitness, it also increases the value of lambda. And what we use is we design a potential function that takes into account both the fitness and the logarithmic factor of lambda. And to some maximum. And also the fitness has another property, is the potential has another property, that the fitness is always greater than the potential. And what we do is study how these three steps, how they behave and the probabilities of each step. And we can see that two of the three steps help the potential. And overall, the probability is greater, making the potential grow over time with a positive drift. And why do we need this maximum consideration for lambda? Well, we want the potential to give us information about the fitness, but right now we only know that the potential grows over time, but we don't know if it grows because of lambda growing or the fitness growing. And with this maximum in the consideration of lambda, we can be sure that the potential is always close to the fitness. Later on, what we do is just study and focus the potential. And even though we cannot be sure that the potential will never decrease, overall, we know that the drift of the potential is increasing over time. And also we know that the fitness is always greater than the potential. So whenever the potential reaches a value of n, we know that the fitness also reaches a value of n and the optimum is reached. Finally, we just use drift analysis to calculate the number of generations that the potential needs to increase from any value to a value of n. And we reach to the conclusion that we need expected number, O of n, expected number of generations to reach the optimum.
Okay, and the other statement that we made was that the number of function evaluations was bounded by O of n log n. So how do we prove this? Well, if we pretend that the algorithm was elitist, so if we had a plus strategy instead, we could use a proof from previous work by Jörg Lessig and I, saying that the expected number of evaluations of the self-adjusting elitist version, so 1 plus lambda EA on OneMax, is O of n log n. And this proof uses that every fitness level is reached only once. But this property is not guaranteed for non-elitist algorithms because, well, we can have a drop in fitness and then go up again. And so we can reach the same fitness level many, many times. So the proof breaks down for the self-adjusting non-elitist 1 comma lambda EA that we want to analyze. So what are the challenges in analyzing this comma strategy? We know that if lambda is small and we're close to the optimum, there is a risk of a fallback in fitness if all the offspring are worse than their parent. And well, we can never be safe because even if lambda is not small, it can decrease exponentially fast at any time. And standard analysis techniques don't work to get this scenario under control. So what we were doing instead is we looked at our previous analysis on the number of generations. And let's look more closely into how the potential and the fitness develop over time. So we know that there is this positive drift in the potential. So if we look at what are the chances of the potential going down at some point in time in the future by something logarithmic. This would mean that the algorithm would have to fight against the drift pointing up over a prolonged period of time. And we show using the negative drift theorem that this has got a very small probability of ever happening. And because the fitness is quite close to the potential, we also get that the probability of the fitness decreasing by something logarithmic is also very small. So small that we can in fact just assume that this doesn't happen in a typical run. And what we then get is a lower bound on the fitness that applies with a very high probability. So we know that the fitness will never decrease below this value at any future point in time. And then now, if the current fitness increases, also this lower bound increases. If the current fitness decreases, this lower bound remains the same, and so on. So what this in fact does is that it turns a non-monotonic function like the current fitness that can go up and down, it turns it into a monotonic function that can only go up in one direction. And we call this a ratchet argument, because in a ratchet also you can only move in one direction. But we still need to prove that we've got these increases in the lower bound and that we advance towards the optimum. So the current fitness could decrease by a bit, but what we can show is that with a constant probability, we'll have a good sequence of generations where we're making good progress towards the optimum. So with constant probability, lambda increases to a safe value and lambda remains safe for at least log n generations. So then we have a period of temporary elitism where then the fitness will increase enough such then we reach a new best so far fitness, which is by log n larger than the previous one. And also the lower bound then has gone up by log n. So we've cranked the ratchet and this lower bound has increased by log n. And then we just iterate this argument over and over again until we can guarantee that we found the best fitness of n. And one key observation here is that, well, the number of times that we traverse a certain fitness level is just a constant during these elitist periods. And that's going to help us to bound the number of evaluations of the 1, lambda EA as the number of evaluations during the elitist periods and those outside elitist periods. This latter is bounded by O of n log n, because then typically lambda is small, it's just logarithmic. And during these elitist periods, we use this fact that every fitness level is reached only a constant number of times. And we do apply the previous analysis for the elitist version of the algorithm. And we know that this value here is bounded by O of n log n. So in total, we get an O of n log n bound for the number of evaluations.
In our work, we also show that the success rate as the limit in the success rate that we imposed before is not only a mathematical quirk, but it's also important because if S is large enough, in this case, if S is larger than 22, then with overwhelming probability, the algorithm will take exponential time to optimize OneMax. And well, why those large success rates fail? Well, coming back to the figure that we had before, where we have the state of the algorithm and the three possible options. If S is large, then f to the 1 over s is much smaller than f, which means that in a successful generation, you will decrease lambda significantly, and in an unsuccessful generation, you will increase it just by a small amount. Everything together, it gets worse when you are at a linear distance of the optimum, because successes are really common. Therefore, lambda will be decreased really often during the optimization. And this makes the algorithm unable to maintain a healthy value of lambda. And there is a negative drift away from the optimum in these points. What we managed to show is that there is a large set of states where this happens, where there is a negative drift. And whenever the algorithm tries to reach a point in this set, the algorithm is pushed back by the drift towards the lower left corner. And this is repeated over and over again. And we can show with the negative drift theorem that for the algorithm to push against this negative drift, it will take exponential time to reach the other side of the of this set of states. But once it reaches that point, it is able to optimize OneMax efficiently and get to the optimum quickly.
Okay, so to conclude our talk, we've shown that simple success-based rules can work for non-elitist EAs. So if the success rate S is at most E minus 1 over E, then we get O of n expected generations and O of n log n expected evaluations, which is best possible for mutation-only EAs. The success rate is crucial because if S is at least 22, then we get exponential times even on the very simple function OneMax. And the reason is that the algorithm stagnates far away from the optimum. Future work would be to close the gap between the efficient and the inefficient regimes for S, and to study self-adjusting 1, lambda EAs on multi-model problems. We've already done this after we submitted this GECCO paper. We've produced another paper that's currently under review, where we've shown that the self-adjusting 1, lambda EA excels on the multi-model problem cliff, in a sense that it reduces the best known upper bound for conventional EAs from O of n to the 25th to O of n log n. So this really shows the power of parameter control. Thank you.